So we'll look at the floating point standards by IEEE, and this is a standard number, like that in Türk Standartları Enstitüsü, TSA, or CE, Certificate European. These are all standards, or anything like when you buy, any kind of product, there's a standard for this. And this is the standard for representing floating point numbers, and this was established in 1985, okay, for floating point arithmetic. And before that, every CPU basically producer had their own format, okay. But now with this standard in place, okay, now this is supported by all major CPUs, okay. And this standard was driven by numerical concerns, okay, which has nice standards for rounding, overflow, and underflow. But as we will see, this is something that's very hard to make fast in hardware. Okay, and you can see that in this committee, the numerical analysis dominated over hardware designer in defining the standard. So whenever as we discuss this representation, keep in mind all these concerns. So here is the standard. Okay, so the floating point representation has this basic form, and then let me just show you here. So here's our fixed bits basically portion, and in this one we need to represent three things. Okay, one is the sign. Okay, usually when we say plus or minus, well, this is the first part, and then we have the M, which is this is about the sign. Then we have the M, which is what we call the significant. This is the part, if you remember, level 6 or 2. This was the significant order. And then there's this 2 is implicit. And then we have this exponent, E, which is basically means 2 to the power E. And we assume here that the significant M, okay, is a fractional value between 1.0 and 2.0. And you know that in scientific notation, you don't have, instead of writing 60.2 times 10 to the power 22, you say that's not normalized, and you change this to 6.02 times 10 to the power 10 to 3. So this, we say that this portion should always be less than 10. Now with this, then the challenge is how we represent these three parts, like this S, M, and E. How do we represent them in binary? So here's the encoding. Remember that we had this fixed representation, and we will use one bit, okay, as the sign bit. Okay, we usually use the most significant bit for this. And you can see that by looking at this -1 to the power S, with this you can see that if S is 0, this means that it's a positive number, okay, because it's -1 to the power 0. If S is 1, then it's negative. And you can see that, why we choose that. It's because you can see that in the 2's complement form, we also had this most significant bit determining the sign of the number, and this kind of nicely fits that. And then we have the exponent bits. Now the exponent bits encodes E, but it's not equal to E. Okay, and we'll see how what this means. Okay, meaning that exponent, this is the bit pattern that we have in this region, in this number of in this basically range, and then then we will, from this we will compute E, which is the exponent, and then we have the fraction part, and this one encodes M but is not equal to M. So we have different precision options. The first one is single precision. This is what we use in float representation. Okay, remember, float takes basically 4 bytes, which is 32 bits. And within that, we use 1 bit for the sign, 8 bits for the exponent, and the remaining 23 bits for the fraction. And when we go to double, which uses 8 bytes, okay, then we have 1 bit for sign, 11 bits for exponent, and 52 bits for fraction. So you should basically know this, you should memorize this. And then there's also the extended precision for Intel machines, where it's temporarily extends the precision of floats into 80 bits, where it uses 15 bits for this and 63 or 64 bits for the fraction. When we represent it, the representation is actually kind of takes three parts. Okay, remember that we had this part, we had the sign, okay, and the exponent, and then the fraction. Okay, and with them, then the representation is kind of pretty straightforward. Let me see how we can do this. Okay. So we represent, the representation works in three different modes. Okay, I'll write it here. So the first one is, it's called, talk about the normalized. So we have the normalized mode, okay, we have the denormalized mode, and we have the special numbers, special values. Each of them are basically, each number can be represented in one of these forms. And in the normalized, in the normalized mode, we assume that exponent bits is neither all zeros and exponent is also not all ones. And in here, then we represent the numbers as the following. Now let's think about this exponent part. Remember that I have a number of bits here. Okay, let's say that I have e bits. And with e bits, now with this exponent, I want to represent what positive exponents and negative exponents. Remember, I want to represent 10 to the power, say 2 to the power 23 or 2 to the power minus 23. And I should be able to represent them in here. With this, we assume that e bits, what's the range of numbers, the binary numbers that we can represent? Well, with this, I can represent from 0 to 2 to the power e minus 1. Okay, I can represent numbers from 0 to 2 to the power e minus 1. Okay, that's where e is the number of bits. But I don't want to, this is essentially the unsigned representation of this. Now, what I want to do is I want to make some of them to represent negative numbers. And so what if, I define a bias, okay, where this would be below this should represent the negative numbers and the rest should represent the positive numbers. Okay, so what should be this value? So we call this value as the bias. Okay, and this should be, the halfway in between. And this bias is defined as 2 to the power e minus 1 minus 1. So if the value, if the bit representation in the exponent part, in the x part, is greater than this, I have a positive, basically, value, otherwise it will be negative. In normalized part, I define, remember, like what I need to do is, like my representation is, minus 1 to the power s times m times 2 to the power e. We know this, right? I know what s is, no problem. And then e and m, that's what I need to do. So what I define here is, I can define e as the following: exponent in binary, okay, minus bias. So exponent, whatever the number of bits that whatever the bits are. Bias, this is a fixed number, which we compute in here. And I define m as, well, 1 dot frac. What I mean, like a what? So I assume, in this case, note that, I assume that there is a 1 here. I just say, whatever the fraction bits are, I will use them as in here. And why do I do this? Why do I assume a 1 dot frac? It's because it gives me 1 extra bit. Remember, in the case of, like the decimal case, I had 6 dot something, right? Because I don't want it to be 0. I don't want it to be 10. So it can be between, it can be between 1 and 9. But in here, it can only be 1. It cannot be 2. It cannot be 0. So let's just assume this implicit. And once we assume that it's implicit, then it's you just gain 1 extra bit, okay, which doubles the range that you can represent. So it makes sense to have this, 1 dot frac assumption, okay. And with this, so let me write this in here. So this one is kind of assumed. And basically this gives us free extra bit for representation. Okay, we'll do some examples in here. Now let me go to here. Now with this representation, it's nice, but there's one number that I cannot represent. Okay, can you tell me which number I cannot represent with the normalized representation? I cannot represent 0. Whatever I have here, it will be non-zero. Okay, because I have this one dot frag. So that brings us to the denormalized portion. In the denormalized portion, and we can determine a number whether it's in which mode is by looking at the exponent bits. If the exponent bits are all zeros, then we say that that number is in denormalized mode. And again, we represent the same thing, s times n times to the power e. And in this particular case, we assume that 1 minus bias, and then I assume m as 0 dot frag. Now this gets confusing, right? It's the first thing that you would note is, in this case, when e exponent is all zeros. Now you can say that here the exponent bit here, this cannot be 0. The minimum that you can have as the exponent will be 0, 0, 0, 1 and minus bias. When exponent is all 0, I would have expected, when in this case the exponent bits are 0. So I would have expected a 0 here, but instead I have a 1 here, which is confusing. Okay, let's make note of this. And the second thing is for the m, now instead of assuming a 1 dot, I assume a 0 dot frag. Now this obviously solves the problem. When I have 0 dot frag, by setting the frag as 0, then I can have actual 0, which is nice. But again, how this 1 minus bias kind of plays into the makes things complicated is still not resolved, but we will get over this. Okay, so now let's go to the third part, which is the special values. In the special values, this is the case when my exponent bits are all ones. In this case, if my frag bits are all zeros, then it represents plus or minus infinity. Yes, we have an explicit representation of plus and minus infinity. And how do you know whether this plus or minus comes from? Well, this is determined by, remember, minus 1 to the power s, right? So with the sign bit set, I can have, plus infinity or minus infinity. Else, which is the case where your frag is not equal to all zeros, then the value is NaN. And I'm sure maybe you have seen this once in a while, which stands for not a number. So we have a representation for not a number. And when do we expect to get this? We expect to get this, for example, when you try to get the square root of minus 1. Or if I try to do infinity minus infinity, or infinity times 0. So whenever you do one of these things, then you'll get not a number as your result. Let's see how this works out. So what you have to remember is, well, we represent our fixed bit representation in 3 parts: sign bit, exponent bits, fraction bits. And with the exponent bits, we treat it as if it's an unsigned number, but there's a bias. So if it's below the bias, then we get a negative number. If it's above the bias, then it's a positive number. And with the fraction, then we treat them as with 1 dot frag or 0 dot frag and so on. And then we have these special values.